Hello, welcome to today's lecture on techniques of integration, integration by parts, and u-Substitution. We're going to start by first talking about integration by parts, and then we're going to talk about u-Substitution. Now, it turns out that both these techniques are based on rules for derivatives. Integration by parts is based on the product rule, and u-Substitution is based on the chain rule. It's really, integration by parts is really doing the product rule backwards, and u-Substitution is doing the chain rule backwards. Here in this slide, we'll define integration by parts for indefinite integrals. We have two functions, f and g. And if you recall the product rule, it says the derivative of f times g is equal to f prime times g plus f times g prime. So multiply the derivative of the first factor by the second factor, and then add the first factor times the derivative of the second factor. When we integrate both sides, so what we're doing is we're adding an integral to both sides of this equation, and then, of course, dx, because when you put functions in the integrand, you need to put dx. Rules of indefinite integrals say that the indefinite integral of a sum is the sum of the indefinite integrals. Now, let's look at the term we have on the left-hand side. The indefinite integral of f times g prime, well, what is that really saying? This is saying anti-differentiate the derivative of fg prime. Well, the antiderivative of any derivative is just going to be the original function. That's why this indefinite integral is going to be f times g. That's, of course, ignoring the constant integration. It's for now, because we're not going to have it all the time. So f times g is equal to f. So f times g equals the antiderivative, or indefinite integral, of f times g prime plus the indefinite integral, or antiderivative, of f prime times g. When we solve for f times g prime, we get the integration by parts formula. The antiderivative of f times g prime is equal to f times g minus f prime times g. Minus the antiderivative of f prime times g. So what really happened here is we took this prime off of g, where we get f times g, and then in this formula here, this prime was taken off of g and placed onto f. Now you can also write this with uv notation. uv is sometimes used for the function g. dv then just means the derivative of the function g times dx. And u is sometimes used the notation for the function f of x. In this case, du is equal to f prime of x times dx. The integration by parts formula then becomes, because g prime times dx becomes dv. Of course, f is u, so it becomes the indefinite integral of u dv is equal to u times v. This is just the product of the two functions, f and g, minus v times du, and that's because f prime times dx became dv. Our goal is that this integral should be easier to evaluate than the original integral, fg prime. Here's an example. Let's use integration of parts to compute an indefinite integral. Let's compute the indefinite integral of x times e to the 2x dx. In this case, we're going to determine, our first step is to determine f and g, or equivalently u and dv. We're going to choose f to be this function x, and g to be this function e to the 2x. In this case, g prime, of course, this function f is the function x, g prime is the function e to the, that should have been e to the 2x, not e to the x. In this case, the antiderivative of e to the 2x is 1/2 e to the 2x. And of course, the derivative of the function f of x is equal to x is just the function 1, the constant function 1. The derivative of any constant multiple of x is that constant. Next step is to plug all terms back into the integration by parts formula. F of x times g of x is equal to 1/2 times x times e to the 2x. And the integral of g times f prime of x dx is equal to 1/2 e to the 2x dx. So notice here, g is this function, 1/2 e to the 2x, and f prime is just 1. So the integrand here is really just 1/2 e to the 2x. We can pull this 1/2 outside. So 1/2 was pulled outside of the integrand, and we're left with the indefinite integral of e to the 2x dx. So the antiderivative, or indefinite integral, of x times 2 to the x is equal to 1/2 x e to the 2x. This is the product of the two functions f and g, minus, so now what happened, we pulled the derivative off e to the 2x and placed it on x. When you differentiate x, you get 1, so we're subtracting 1/2. We are subtracting 1/2 times the antiderivative of e to the 2x dx, or equivalently the indefinite integral of e to the 2x dx. Let's continue this process of computing the indefinite integral. When we ignore the constant of integration, we can compute the, so this is just for now, we ignore, as we've seen before, we ignore the constant of integration, and we compute the antiderivative of f prime times g. It is 1/2 e to the 2x dx. The antiderivative of e to the 2x is 1/2 e to the 2x. You multiply it by the 1/2 that lives outside, 1/2 times 1/2 is equal to 1/4. So we're left with 1/4 e to the 2x. We plug this function back into the integration by parts formula and add the constant of integration c. So the integral of x e to the 2x is f times g, 1/2 x e to the 2x, minus 1/4 e to the 2x. That's what we got from integrating f prime times g, plus the constant of integration c. Now that was for indefinite integrals. For definite integrals, the formula is slightly different, but very similar. If f and g are both functions, continuous and differentiable on an interval, the integration by parts formula for definite integrals is the following. The definite integral from a to b of f of x times g prime of x dx is equal to the difference between f of x times g of x evaluated at b, f of b times g of b, minus f of x times g of x evaluated at a, f of a times g of a, minus the derivative now is taken off of g and placed on f. So it's, again, the definite integral from a to b, f prime times g. So notice these bounds, the lower bound and upper bound, doesn't change. And again, the hope and the goal is that this definite integral, f prime times g, should be easier to evaluate than this definite integral, f times g prime. Here's the problem. So as before, let's have our integrand be the same function, x e to the 2x. And we saw in the previous slides that we could choose f to be x and g prime to be 2x. That means g is 1/2 e to the 2x and f prime is 1. Their product, of course, f times g is just 1/2 x times e to the 2x. Now here, the lower bound, of course, what is the lower bound? It is 0. What is the upper bound? It is 1. So that means b is 1 and a is 0. We compute f of 1 times g of 1. That's just plugging in 1 to this function here. 1/2 times 1 times 2 times 1, which is 1/2 times e squared. When we plug in 0, we get f of 0 times g of 0, which is 1/2 0 times e to the 2 times 0, which is just 0. 0 times any number, of course, is 0. So f of 1 times g of 1 minus f of 0 times g of 0 is just 1/2 times e squared. When we plug this back into the integration by parts formula for definite integrals, we get 1/2 e squared. That's f times g evaluated at the upper bound minus f times g evaluated at the lower bound minus 1/2 times definite integral from 0 to 1 e to the 2x dx. And again, that's just from the fact that g times f prime was, of course, 1/2 e to the 2x. We pulled the 1/2 out of the definite integral, just from rules for definite integrals. Let's continue this process. Notice that 1/2 e to the 2x is an antiderivative of e to the 2x. And when you evaluate it at 1, we get 1/2 e squared. When you evaluate it at 0, this function at 0, we get 1/2. Its difference, therefore, if you pull out this 1/2 factor, is 1/2 e squared minus 1. That means that the definite integral from 0 to 1 of e to the 2x times dx times 1/2 is equal to 1/2 times 1/2 times e squared minus 1. Distribute 1/2, we get 1/4 times e squared minus 1/2. That's because this 1/2 got distributed to here. And we multiply that by 1/2, so we get 1/4 e squared minus 1/2. We're going to plug this expression back into the formula for the integral from 0 to 1 of x e to the 2x. What do we get? We get 1/2 e squared minus 1/4 e squared minus 1/2. Now notice 1/2 e squared minus 1/4 e squared, that's the same as 1/4 e squared. We add 1/2 because when this negative is distributed, to each term, it makes this negative positive. Negative a half is the same as positive 1/2. That's why we're adding a half. And of course, 1/2, which is 2/4 minus 1/4, is equal to 1/4. So there you have it. The definite integral from time of x times e to the 2x is 1/4 e to the e squared plus 1/2. And that was obtained from using the integration by parts technique. Now we're going to go on to the technique of u-substitution. Let's recall the chain rule. If we have a composite function that consists of an outside function f and an inside function g, then its derivative is f prime, the outside function, f prime evaluated at g of x times the derivative of the inside function. So it is the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. Now, as before, what does this mean? This means the composite function is an antiderivative of a function that looks like this. A function that looks like the derivative of some outside function evaluated at an inside function times the derivative of that inside function. So, the indefinite integral of f prime evaluated at g times g prime is equal to f of g of x plus c. Okay, well, how is this going to help us with evaluated integrals? Let's set u to be equal to g of x, the inside function, and du equal to g prime of x dx. Then we can rewrite the above equation as follows. The indefinite integral of f prime of u du is equal to f of u plus a constant. And as we'll see, this technique of u-substitution is used if the integrand, what's inside of this integral, looks like a function evaluated at an inside function times the derivative of that inside function, or maybe some multiple of it. Let's see an example. If we compute an indefinite integral using u-substitution, let's compute, for example, x times sine of x squared. So here, if you notice, sine looks like an outside function, x squared looks like an inside function. The derivative of x squared is 2x, and a multiple of it, x, appears in the integrand. So that means we're going to do the first step, which is to set u to be the inside function, x squared. Next, we're going to compute du. That just means differentiate the function u, and then tack on a dx at the end. Now, the second step is to solve for the remaining factor in the integrand. What's the remaining factor in the integrand? Well, we have an outside function evaluated at an inside function, sine evaluated at x squared, but the other factor in the integrand is x times dx. We have du is 2x times dx. So we're going to solve for x dx, which is equal to 1/2 du. Of course, that's just from dividing both sides of this equation by Next step is to rewrite the integral in terms of u. Sine of u times 1/2 du is equal to 1/2 times sine of u du. That's just from pulling out the 1/2 from the indefinite integral. And now the fourth step is to evaluate the indefinite integral by considering the integrand as a function of u. 1/2 integral of sine of u du is equal to negative 1/2 cosine of u plus a constant. That's because the antiderivative of sine of u is equal to minus cosine of u. We've seen that formula before. Right? If you differentiate cosine of u with respect to, or negative, if you differentiate negative cosine of u with respect to u, what you get is positive sine of u. The second step is to plug in the original formula for u as a function of x into the expression on the right-hand side. So we're plugging in to negative 1/2 times cosine of u. What do we get? We get negative 1/2 cosine of x squared. And indeed, you can check this. Negative 1/2 cosine of x squared plus a constant, its derivative will indeed be its derivative will indeed be sine of x. So x times sine of x. So our conclusion is that the antiderivative of x times sine x is equal to 1/2, negative 1/2, times cosine x squared plus a constant. Now here's the u-substitution formula for definite integrals. F prime of g of x times g prime evaluated from a to b. Let's set u to be g of x and du to be g prime of x. When x is a, u of x is equal to u of a. When x is b, u of x is u of b. The definite integral becomes the definite integral from a to b of f prime of u times du. Here, f of u is an antiderivative of f prime of u as functions of u. So we have integral from a to b of f prime evaluated with g of x which is the same as definite integral from a to b of f prime of u times du, which is equal to f of b minus f of a. So it's important here. So sorry, this should have become, so from a to b. So this upper bound here should have become u of b, and this lower bound here should have become u of a. So what's important here is that the lower bound changes. The lower bound and upper bound changes. And actually, it's not necessary in this case to plug back in u as a function of x. We can just integrate this as this definite integral f prime of u du as a function of u. Let's look at an example. So let's compute the integral from 0 to square root of pi over 2, x times sine of x squared dx. Solution is to set u to be the inside function. Again, we saw that before. Inside function here is x squared. Du then is 2x dx. So x dx is equal to 1/2 du. The integrand, as we saw before, becomes 1/2 sine of u du. So when we plug in u of 0, that means we plug in 0 to the function u, we get 0 squared, which is 0. When we plug in square root of pi over 2 to the function u, we get square root of pi over 2 squared. Squaring undoes square root, so we're left with what's inside the radical, which is pi over 2. The lower bound becomes 0, the upper bound becomes pi over 2. So the definite integral from 0 to pi over 2 of 1/2 sine of u, we just forgot the du there, it's not that big of a deal, but times du is equal to negative 1/2 cosine of pi over 2 plus 1/2 cosine of 0. Now, why do we have this negative 1/2 cosine of pi over 2? Well, remember, the antiderivative, or in antiderivative of 1/2 sine of u is negative 1/2 cosine u. We evaluate negative 1/2 cosine u at pi over 2, and we evaluate negative 1/2 cosine u at 0. When you plug in the upper bound to the antiderivative, we get negative 1/2 times cosine of pi over 2. When you plug in the lower bound to the derivative, we get negative 1/2 times cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. We have a plus here because we're subtracting. It's the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So what we're left with is negative 1/2 cosine of pi over 2 plus 1/2 cosine of 0. This is just 0. It's just 0. 0 plus 1/2 is just 1/2. That's why we have 1/2 here as our solution. Okay, so here's the summary. Integration by parts. The integral of f g prime is equal to f g minus integral of f prime g. It's the product rule done backwards. Integration by u-substitution. The integral of f prime g is equal to f prime of u, which is equal to f of u, or f of g of x plus a constant. It's the chain rule done backwards. And so this should have been a small over there. This should have been f prime of g of x times g prime of x. So all right, so that's it for today's lecture. You'll be having a quiz tomorrow on these two techniques, integration by u-substitution and integration by parts.